Okay, so welcome back to another lecture video. So this time I will try to explain the distribution type, the probability density function, or simply the probability distribution for the time to failure. So distribution here also mean the probability density function or probability distribution okay. So both referring to the same thing. Okay, so in a statistic, if you have random variable, okay, and that random variable can be expressed using probability distribution or probability density function. Okay. Let's say for example, like the height of student, okay, in a class, okay, or what else, okay, the time of arrival of customer into a shop, okay. The time in between the arrival of customer into a shop also a random variable, okay, and that can also be expressed using the distribution function. Okay. So similarly, okay, like the time to failure, okay, also a random variable, okay, and therefore there must be a type, okay, a type of distribution function that can be used to express the time to failure. Okay, and okay, as we learned previously, perhaps in your probability and statistic course, okay, what the type of distribution that may have appeared, okay. For example, normal distribution, okay, binomial, exponential, okay, or Poisson. If this one, if it's time, okay, if like the arrival of, for example, like the arrival of customer into a shop, okay, the event occurring in time is usually expressed using Poisson distribution, okay, or gamma, Weibull, okay, log normal, okay, so on and so forth. Okay, so there are many type of distribution, okay, that are used in statistics, okay, and especially in our case, okay, we later we will dive into that later, okay, and the mostly used exponential in reliability study, the mostly used distribution function in reliability study is the exponential. Okay, we will come into that later. So let's say, as following the notation that we use in the previous videos, okay, the time to failure, the distribution, okay, the distribution of the time to failure, okay, is ft, okay, and it's random variable, okay, and our time to failure is random variable. Okay, so ft is our distribution function, or our PDF. Okay. And ft can be uh, can be normal distribution, binomial, exponential, Poisson, gamma, Weibull, normal, so on and so forth. Okay. So it can be any. So depend on depend on uh, depending on your equipment, okay, or depending on your item, okay, or equipment, or your hardware, okay. So the things that you are considering, okay, so depend on that, uh, you will select one type of, okay, or you may select it, okay. So you may, so a type of distribution, a type of PDF may be selected for your equipment, okay, and that's the selection is uh, depend on your items, okay. So let's say in the previous video, okay, we had the bulb, okay. So let's say bulb, okay, from the measurement, okay, let's say from your observation and measurement, okay, you say that the bulb follow exponential distribution. So then your bulbs, the time to failure for your bulbs has the exponential distribution. Okay. Uh, however, okay, however, uh, PDF, okay, is difficult to measure. Difficult to measure. So instead, what is practically being measured is uh, the failure rate function. Okay. So how can we deduce our PDF? Okay. So that is from the measurement of our failure rate function. Okay. And as in the previous video, I don't remember which part, but we had the distribution, the density function is equal to failure rate function. Okay, exponential 0 to t failure rate function du. Okay, so we had this. So from the measurement of the failure rate function, okay, we can deduce our distribution function. So why do we need? So okay, if we can, so if we begin with the measurement of failure rate function, then why do we need the density function? Okay, so why do we need the uh, PDF or the distribution function? Okay, so there are many there are many reasons that can be spelled out here. Okay, first one is we know if we know the PDF, okay, we can we can that will tell us, okay, when when is the failure concentrates. Okay? Like let's say if the PDF is normal distribution, okay, so then that will tell us that at this moment of time, okay, that is when most of the failure occur, okay, or if the normal distribution, okay, and if let's say it's exponential distribution, okay, so then at the beginning at the beginning of the uh, at the beginning of the usage of the item or the component, that's where the failure that's when the failure is concentrating. Okay. So that's the reason number one why we need the PDF. Okay, I am recording. So, okay, so the secondly is uh, so it is for it is for the calculation of the failure probability, okay, because we had the failure probability at time t, okay, which was if you still remember, it's the probability that the time to failure, okay, is less or equal to the time t is equal to 0 t, okay, and this here come your PDF, okay, uh, although you can calculate the failure probability at time t, okay, which is the complement to reliability, so and mathematically it is 1 minus rt, which is 1 minus rt is exponential uh, 0 t zu du. Okay, so even though with failure rate function you can calculate the failure probability, okay, but if you see the expression, this expression, okay, mathematically this is easier. Okay, so that is when you want to calculate the failure probability. The same goes if you want to calculate the reliability. Okay, so although you can calculate the reliability using the failure rate function, okay, the failure rate function du. Okay, so even though you can calculate using the failure rate function, but mathematically it is easier if you calculate y minus ft, okay, or y minus 0 to t f u f u du. Okay, so this one is easier. Okay, so so those two reasons is why you need to decide what is the PDF, what is the type of distribution for our time to failure. Okay. So the time the distribution, okay, the type of distribution is unique for it is unique for the equipment. Okay, so let's say by performing the observation and then use the outcome to develop the statistical conclusion. Okay, then the conclusion will tell you what is the distribution type for the equipment. Okay, so let's say pump. So let's say pump. This is just example. I'm not sure. Okay, the pump, it could be log normal. Okay, or maybe bulb. Okay, in the previous explanation I said it is exponential. Okay, what else? Valve. Okay, valve. Maybe I don't know. Okay, so each type of equipment, okay, is usually governed by a type of distribution function. Okay, so the type of distribution, it become the identity for the equipment. Okay, and so okay, so I'm going to give an example. Okay, let's say the bulb. Okay, the bulbs that I use example in the previous video, but I'm not sure this is appropriate or not. Okay, I'm not sure whether the bulb is exponential distribution or not. Okay, so let's say the bulb is governed by the time to failure of the bulb can be expressed using the exponential distribution, okay, or exponential probability density function. Okay, so up to you how you want to express the distribution. Okay, so mathematically the distribution, the exponential distribution, okay, exponential distribution mathematically has lambda equal to lambda exponential minus lambda t. Okay, and lambda must be a positive integer. positive number, okay, and lambda is called distribution parameter. Okay. So for exponential distribution, we have lambda. Okay, but in other distribution, in other distribution, there are also specific parameters for that distribution. So if you're interested, please check the other distribution. But in this example, I will for the example I will use only the exponential distribution. Okay. And so if it is known that the bulbs follows the bulbs follow the exponential distribution, okay, then the reliability of the bulb at time t, okay, is probability that the time the failure is less or equal than t. Let me check this one. Okay, so that is simply the integration of g to the infinity the exponential distribution du. Okay. And if you perform the mathematics, okay, if you put the exponential distribution, which is lambda exponential minus lambda t minus lambda u du. Okay. So mathematically you will get exponential minus lambda t. Okay. And therefore ft is minus 1 minus rt. Okay. So you get 1 minus e minus lambda t. Okay, so the probability of failure of the bulb at time t is simply 1 minus exponential minus lambda t. Okay, and if the okay, and if ft is exponential, okay, which is lambda e minus lambda t, okay, then what is the failure rate function? Okay, by definition it is the ft over rt. Okay, so ft is minus lambda e minus lambda t. Okay, and rt is simply e minus lambda t. Okay, so the failure rate function, okay, if the time to failure is governed by exponential distribution, is merely the lambda. Okay, so it's constant. Okay, so meaning that if the bulb follows exponential distribution, okay, so the failure rate function for the bulb is just simply a constant, okay, which is lambda. Okay, so at the beginning, okay, I said lambda is the distribution parameter for the exponential distribution, but now, okay, after doing the mathematics here, okay, we can conclude that the failure rate function for exponential distribution is just the lambda. Okay, so lambda here is a constant. So lambda is a constant. Okay, is independent to the time. So for exponential distribution, okay, lambda we call the lambda as the failure rate. Okay, so for exponential distribution, okay, the parameter that you see that you see as the lambda here is the failure rate. Okay, because it is derived from the failure rate function. And in many practical application, okay, in practical application, we uh, we like to assume that uh, the component follow the exponential distribution. Okay, so even though empirically or by experience, okay, in the example of the measurement of bulbs, okay, in the previous video, okay, we had the bathtub curve, okay. uh, this is that okay, sorry, my pen, okay. This is the failure rate, okay. This is the time, okay. uh, we had, okay, at the beginning we had the infant mortality, okay, and then after that uh, this is the aging mortality, okay, because of the wear and tear. This is the aging, this is the infant mortality. So even though in reality, uh, we experience this bathtub curve, okay, but what we can do, okay, or what is actually uh, we are doing, okay, we can eliminate this the high failure rate during the infant mortality, during the starting time, okay, by uh, test testing, okay, testing prior prior to the commission, meaning that if you doing test, okay, checking and test before the item or the equipment is put in operation, okay, you can eliminate the the high infant mortality rate, okay. So uh, practically you making uh, the curve uh, going down, okay. And similarly, okay, after some time when you are approaching the aging mortality, okay, what you can do to shift the curve down are repairs, okay, repairs or preventive maintenance, okay. So by doing repair and maintenance, okay, you can actually uh, pull the curve down, okay. So in the overall effect, okay, is like is can be seen as a constant uh, failure rate, okay. So what I'm trying to say here is that uh, in practice, okay, you can actually assume exponential distribution for your equipment, okay, by introducing the testing prior check and testing before the operation, okay, and doing the preventive maintenance or repair, okay. Our equipment, okay, will follow the exponential distribution, so meaning that its failure rate is constant all the time, okay, which makes that's the reason why in many cases, okay, or in many cases we like to use exponential distribution to express the time to failure to the most of our equipment. Okay, uh, from the mathematical calculation wise, it is easier. Okay, because uh, you will realize if you try to if you compare this argument with this if you try compare this the exponential distribution with other distribution, okay, even the normal distribution, you will find that mathematical wise the exponential is easier to handle. Okay, and uh, as well as its failure rate function is also easier to be handled. Okay, because of the constant failure rate, okay, our calculation will be easier, and plus and on top of that, our practice also leads to the exponential distribution. Okay? So eventually we would like to use exponential distribution. So if okay, I'm going to get this is the last example that I want to talk here. Okay, for example, if you are calculating the time dependent fault tree. Okay, so if you are doing the time dependent fault tree analysis, okay, let's say let's say your system consists of two equipment. Okay, so the failure of the system, okay, is due to the both uh, well, the failure is due to the both to the failure of both your component here. Okay, let's say this is your component number one, this is your component number two, and this is your system A. Okay, and the component one, okay, the failure rate for component one is lambda one. Okay, and the failure rate of component two, let's say it is lambda two. Okay, so the time dependent failure probability of your component one. Okay, so if it is the let's say both component, okay, both component are governed by exponential distribution, okay, with the failure rate lambda one for equipment one and lambda two for the equipment two. So failure probability at time t for equipment one is 1 minus exponential minus lambda 1 t, and for equipment 2 is 1 minus exponential minus lambda 2t. So since this is the AND gate, okay, so the failure probability of the time dependent failure probability of system A, it is the simply the multiplication of failure probability of equipment 1 and the failure probability of equipment 2. Okay, so which is 1 minus e minus lambda 1t, 1 minus exponential minus lambda 2t. Okay, so if you want to try to visualize, okay, the behavior of equipment number one. Okay, so this is failure, but if you calculate the reliability, so it is It is exactly uh, it is, I don't remember if I wrote it or not. Okay, it is exactly exponential minus lambda t, this one. So it is exactly this one. Okay, so exponential minus lambda 1 t. So on the graph, okay, so reliability, okay, at time 0 is the at time 0 it is 1. Okay, this is time. At time 0 it is 1, but uh, with the time, so it will gradually decrease, exponentially decrease, okay, because this is exponential function. Okay, so this is the R1t for the equivalent 1, and as the failure probability is 1 minus reliability, so what you get, failure probability at the beginning at time 0, if you put 0 in this equation, okay, you will get 0. Okay, same goes with RT. If you put 0, it will equal to 1. So failure will exponentially increase with time. For equipment number 1, okay, similarly for equipment number 2, okay, the difference is the difference is only due to the failure rate, okay, or lambda 2. Okay, so so this is the line for F1. Okay, so FA, so what about FA? So FA is, let's say this is F1. Okay, uh, and this is F2. Okay, so this is F2, this is F1. So the results for FA would be down here. Okay, so this is FA. So as the time increase, the failure will increase. Okay, so okay, so why the failure of the system A increase with the time? It is because the failure of component 1 increase in time, and so does the failure of the failure probability of equipment 2. It is increase in time. Okay, so this is very simple for tree analysis. Okay, if the equipment follows the exponential distribution. Okay, so I think that's all for the exponential distribution. Okay, I think the easiest uh, and I also think that the easiest or the simplest uh, time to failure distribution for equipment is the exponential distribution. So if you interested for other distribution, okay, you can check the other distribution by your own self. Okay, so that's all the best in your study.